Hello everyone, this is me Abrar Jamil. I have completed my BSc in Tripoli from Kuwait. Today I am going to give a short lecture on a semiconductor device which is called MOSFET. As we know that the transistors are the basic building blocks of modern electronic devices. Using transistor we can do switching, amplification and many other tasks. Among the transistors, MOSFET is one of the most popular and the widely used transistors. So if we see the full name of the MOSFET, it is metal oxide semiconductor field effect transistor. It may sound like the multiple words are meshed together, but soon we'll actually see how this name makes sense. Anyway, there are actually two types of MOSFET, enhancement type and the depletion type. The major difference between these two types is in enhancement type, the MOSFET is by default off, we need to turn it on, and in the depletion type, the MOSFET is by default on, we need to turn it off. Then these two types are further divided into two types, N-type MOSFET and the P-type MOSFET, depending on the channel that is being formed. Now, going to the structure of the MOSFET, we will actually in this lecture today we'll see the NMOS enhancement type MOSFET as an example. So starting with the structure, first of all, we need to have a P-type silicon substrate that has been yellow colored here, and we will actually connect terminal here. We can call this as the body of the substrate terminal. And at the top of this substrate, we will actually diffuse two heavily doped N-type well, and here those are in green colored, and we can call this as the source and the drain. And in between these two regions, we will deposit a thin layer of insulator as a dielectric media, for example, silicon dioxide. And here is the insulator, and top of this layer we will connect another metal connector. We will call this as the gate terminal. So if you see in this region, that is metal, oxide and semiconductor. So half of the name is already been justified. So we can see that MOSFET is basically 4-terminal device, but in real cases, the source and the body are made short because we need to get rid of one of the most common phenomena in MOSFET, body effect. But that's not what we are going to discuss today. So that's why we sometimes see MOSFET is a 3-terminal device. Now, before going to the working principle, we need to clear a basic concept which is called p-n junction. As we know that in P-type semiconductor, silicon is added with trivalent impurities, and that's why the majority carriers here are hole and the minority carriers are electron. And in the N-type semiconductor, silicon is added with pentavalent impurities, that's why the majority carriers are electron here and the minorities are hole. Now, if we add these two type of semiconductor, electrons from the N side diffuses to the P side and fills the holes. As a result, the holes get negatively charged, and the place that has been left by electron gets positively charged. And that's why there is an electric field induced from the N side to the P side that actually opposes the further flow of electron. And that's why near the junction we get a depletion region here. Now, if we actually connect a battery with positive terminal at the P side and the negative terminal at the N side, then the electric field of the battery opposes the electric field that has been produced in the depletion region. As a result, the depletion region gets minimized here, and we call this as the forward bias. And in the reverse bias, the opposite case occurs. The reverse bias voltage actually increases the width of the depletion region. So here we can get a wide depletion region here. Now, going to the working principle of enhancement type NMOS, our main target is to flow electron from the source terminal to the drain terminal. That means the conventional current from the drain to source. That's why we will add a battery with positive terminal at the drain side and negative terminal at the source side. We will call this as VDS. Now, we can see that in the junction of N and P, the depletion region will already be present here. Now, if we increase the VDS, then in this region the junction is already in reverse bias, and if we increase the VDS, the depletion will also increase. So we will not get any flow of electron from the source side to the drain side here, because of the depletion region. Also, there is no channel being formed. So to create a channel, what will we do is we will add a battery in between the gate and source side with the positive terminal at the gate side. So here we will call this as VGS. Now what will happen, due to the positive terminal at the gate side, the positive charge will accumulate here, and this positive charge will repel the holes at the P side. So the holes at the P side will get moved away from the gate side, and as a result, near the gate the fixed minority electron will accumulate, and this will gradually form the channel. If the value of the VGS exceeds a certain amount of voltage, then the channel will get perfectly formed and the type of the channel will be N-type, and we'll call this certain amount of voltage is V threshold. So to form a channel, VGS should be greater than or equal V threshold. So here a channel has been formed which is N-type channel, and for this, if we now increase the VDS, the electron will go from the source to drain, and we'll get another current whose direction is from the drain to source here. We'll call this as ID. Right. Now if we if we see a graph which is ID versus VDS, that means drain current versus drain to source voltage. So first of all, say the gate to source voltage is lower than the threshold. Then what will you see? We'll get no current, right? Because due to no channel, so we'll call this as the cutoff region. Now, if the VGS voltage is greater than the V threshold, then if we increase the VDS voltage, then current will obviously increase, right? But will it continue like this? I mean, in this region, the current is increasing linearly, that follows the ohmic law. But will this continue further? But actually, it's not, because we already showed that due to the increasing of VDS here at the drain terminal, the depletion width is also increasing, and this depletion width actually move toward the drain terminal, which gradually narrow down the path of the electron. As a result, the current can't increase as the VDS increases, and at a certain point the channel will perfectly get pinched off, but in real case it doesn't get pinched off. As a result, the current doesn't get increased, it becomes constant, and we get a saturation point here. And then if we increase VDS, the current gets saturation, and we'll call this as a saturation region, and before that we get a triode or linear region. Now if we want a higher amount of current at certain VDS voltage, what can we do? Because the current has already get saturated. For this, what we can do, that we already know that the gate to source voltage actually controls the channel. So increasing this gate to source voltage, we can get a wide channel, and this wide channel, because a more electron will accumulate here, and because of this wide channel, the number of electrons will get also increased. Now if we increase the VDS voltage, the current will also increase, and as the channel has get widened, so we will get a higher VDS to get the saturation current. So for the increased VGS voltage, say it is VGS 3, and which is higher than the VGS 2, then if we increase the drain to source voltage, the current will also increase, right? And thus, if we increase the gate to source voltage further, then the current will also increase. And this is the ID versus VDS characteristics. And if we wanna see the transfer characteristic, that is input voltage VGS, the output current ID, so before threshold we will actually get no current, right? Because there is no channel. And then if the gate to source voltage exceeds the threshold voltage, then we will get current exponentially. So this is the transfer characteristics. Okay, and now we can see the symbol of the MOSFET here, that is P channel for the N channel and enhancement type depletion in general. So in general, we can see that the current is from source to drain, and for N channel the current is from drain to source. Okay, so we can see that this is the overall operation of the MOSFET, and we can see the MOSFET in our modern electronics too much. So that's all for today. Thanks for staying with me and showing the thirst for learning. Thank you.